How much do you know about climate change? That we're heading for 3 or 4 degrees Celsius of warming? That although it's difficult to predict the impacts of climate change, the scientists are quite good at forecasting future temperature increases? That maybe if we stop adding CO2 to the atmosphere tomorrow, within a few decades the oceans and the plants would absorb a lot of the CO2 and temperatures would start to go down? What if that wasn't true? What if instead we were heading for a temperature increase of 10 degrees Celsius? That even if we stopped adding CO2 and became net zero tomorrow, the Earth would warm for centuries to come. This isn't a count everything conspiracy theory. These are all concerns of Professor James Hansen, one of the world's most respected climate scientists. This video is all about one piece of research that he and his team have carried out. I warn you, the Count Everything channel is famous for its dull but worthy videos. This video is especially dull, but I've taken so long researching it and trying to understand the concepts, I'm too emotionally attached to it not to upload it. But on the upside, I get lots of comments about why doesn't the United Nations take into account feedbacks from melting ice. This video does cover that subject, so try and stick with it if you can. This whole video is about what would happen to Earth's temperature if we were to double the amount of CO2 in the atmosphere. It's one of the oldest, most fundamental parts of climate science. It's still unknown, and there's still concerns that it may even be the wrong measure to use. The philosophical question about what happens to global temperatures if we were to double the amount of CO2 in the atmosphere goes back to 1896. A Swedish chemist asked the question, and he knew you couldn't just do an experiment in the laboratory to see how much heat CO2 trapped, because he knew a warmer atmosphere would contain more moisture and that water vapour was a greenhouse gas. So he spent a year thinking about it. He did nearly 100,000 calculations by hand, and he came up with the estimate that if you double the amount of CO2 in Earth's atmosphere, then you get a temperature increase of between 5 and 6 degrees Celsius. Later on he refined his estimate and said it was only 4 degrees Celsius. That's an important number to remember, 4 degrees Celsius. Fast forward to 1979, and an American meteorologist, Joel Charney, asked the same question, but he defined it much more formally. He said, what happens to Earth's temperatures if you double the amount of CO2 in the atmosphere and you only take into account fast feedbacks, what he called fast feedbacks, so the amount of water vapour that changes, melting of sea-based ice, not land-based, sea-based ice, and changes to clouds. And he explicitly excluded land-based ice and any additional greenhouse gases that might be generated from the warming, because he considered those to be slow feedbacks. And in 1979, people were just interested in, is climate change happening? And if it is it being caused by humans? So they wanted like a generic value for doubling CO2 that would apply to any situation, not just one particular place in time or one particular climate. And it's called equilibrium climate sensitivity. Here Professor Hansen writes the definition that we'll use for the video. ECS is the climate sensitivity defined by the Charney study with ice sheets and greenhouse gases fixed. Okay, so they don't accept any feedbacks from ice sheets and greenhouse gases. And to understand it, before we get into the controversial aspects, to understand it, we're going to need my world famous zero-dimension energy balance model. It's a single equation, but it's accurate enough to tell you Earth's average surface temperature. All you need to do is tell it how much heat energy the Earth receives from the sun, and it comes in the form of shortwave infrared radiation. You tell it how much of that heat energy is reflected straight back into space, either by the ice sheets or the clouds. Because the Earth's surface is being warmed by the sun, it's effectively glowing. You can't see it, but it's emitting its own long wave infrared radiation, and it's emitting heat back out into space. And then you put in a value for the greenhouse gases and clouds, and that tells you how much of the Earth's heat that it's emitting is trapped and gets reflected back down and causes warming. And this energy balance model assumes the amount of energy arriving from the sun, the amount of heat energy arriving from the sun, and the amount of heat energy being emitted by planet Earth are identical, because it's in balance. It's a balance model. If you were to suddenly double the amount of CO2 in the atmosphere, suddenly a lot of the Earth's infrared heat energy is blocked by the greenhouse gases, because this is how climate change is being caused by humans. The additional CO2 blocks Earth's long wave radiation, its heat energy being emitted into space, and so you have an imbalance. There's more heat arriving than is going out, and so planet Earth starts to warm, or at least the surface starts to warm. And as the surface of planet Earth warms, it emits more long wave infrared heat energy, and every day it gets warmer and warmer, and eventually it's producing so much infrared heat, long wave infrared heat, that the amount of energy going back out into space eventually matches the amount of energy coming from the sun, and the Earth is in balance, or is in equilibrium. I think that's how you pronounce it, equilibrium. But the Earth's surface is warmer by that time, but at least it's back in balance and it won't carry on changing. So this is what the philosophical discussion is, and after nearly 130 years, nobody's really quite sure, even though it's the most fundamental question that a lot of climate science is based on. There's one new factor we need to take into account. If you think in a normal climate change, for example, if an ice age warms up, enters a warm period, if there's even during a great extinction period, like the PETM, the Paleocene, Eocene thermal maximum, which is a great extinction period, even then the rate of heating is quite slow. So Earth is never that far out of balance. Earth's energy is never that far out of balance. If you suddenly double the amount of CO2 in the atmosphere, suddenly there's a great imbalance, and it will take planet Earth quite a long time to heat up, so it's able to produce enough long wave infrared radiation to blast it into space, so it's in balance with the sun. This is a new issue that the scientists are just starting to take seriously, and it's more complicated than it sounds, because it's not linear. You get the greatest amount of warming. If you double the amount of CO2 in the atmosphere, you get the greatest amount of warming on day one, because suddenly you've got all this extra heat trapped, but planet Earth's surface hasn't had time yet to heat up and start emitting increased levels of long wave infrared radiation. Well, as you get a temperature increase, Earth is able to emit more and more long wave radiation, and so the energy balance gradually gets less and less, and the increase in temperatures therefore sort of flattens off. So the first day you get a really sharp increase, sudden shock, all this CO2 in the atmosphere, and then as you gradually reach the point of equilibrium, the actual forcing, which scientists call the amount of extra heating that's being applied to the Earth's surface, the amount of forcing gradually gets less and less, because planet Earth is emitting more and more long wave infrared heat energy into space. So the point I'm trying to make is, which you'll need to remember later on, just because we've got one rate of heating now in April 2023 doesn't mean we're going to have the same amount of heating later on, and you need to be aware of that, which you'll realise why it's important later on. And scientists call the time between the CO2 doubling and the Earth reaching its equilibrium point as the response time. Can you see now how clever the climate scientists are? How intuitive it is, how easy it is if you think about it, but you have to think about it. Now we come up to modern times. Now you're fully qualified in energy balance models and equilibrium climate sensitivity, one of the founding parts of climate science, one of the oldest parts, which is still not resolved. And now we'll look at what the United Nations is doing, or what it thinks its value for ECS, I call from now on equilibrium climate sensitivity. I'll call it ECS to make it easier on me. But we'll see now what the United Nations thinks about ECS. Whenever I say United Nations in this video, what I really mean is the United Nations Intergovernmental Panel on Climate Change Assessment Report number 6, Working Group number 1, which is all the physical aspects of climate change. Let me find my notes now. This is what the United Nations has to say about equilibrium climate sensitivity. Uncertainties in the ECS and other climate sensitivity are the dominant source of uncertainty in global temperature projections over the 21st century under moderate to high greenhouse gas emission scenarios. It's 130 years old. This measure is really vital for our understanding of future warming. And do you know how the United Nations has been trying to estimate ECS all this time? It's been using models, 3 different types of model: atmospheric models, fully coupled ocean atmosphere models, and Earth system models. Well, if you saw the previous video, you'll know models are very good to say climate change is definitely happening and it's definitely being caused by humans. Beyond that, it's not quite so useful. For the last 30 years, the United Nations has been using models for its reports for ECS. This is what it's decided in the most recent report. Global warming in climate models over 1850 to the present day exhibit no correlation with ECS. You have to admire the United Nations' dogged determination to carry on using models, even though they don't have any relation to the real world, to calculate one of the most fundamental, most important aspects of climate change for predicting future warming. Not only that, but as the climate models are becoming more sophisticated, they're gradually producing a wider range of possible values. 8 years ago, the models thought it was just over 3 degrees Celsius. Now the models think it's just under 4 degrees Celsius, 4 degrees, the famous number. The United Nations is doggedly sticking to 3 degrees Celsius, and they're saying they're assessing it. They're not just blindly following the models. And also, they're taking in more sources of information. In assessment report number 6, the assessments of ECS are made based on multiple lines of evidence, with Earth sensitivity models representing only one of several sources of information. So what that means, I think, is they're looking at the real world, and if you look at this table, the real world they're looking at are ice ages and warm periods, because you can go back 800,000 years of climate by using ice cores that have been extracted from the Antarctic. And the ice cores contain bubbles of air which contain the greenhouse gases at that period, and because CO2 spreads itself quite well all the way around the world, just taking it from one site in the Antarctic is fine to get a good estimate of CO2 values at that time. You can also get an estimate of temperature by looking at the isotopes of oxygen and hydrogen, which make up the water that's formed the ice. But you have to do a bit of adjustment, because everyone knows the Antarctic's cold, the equator's hot. So you have to do a bit of adjustment to get an idea of global temperatures. But both Professor Hansen and the United Nations agree that the difference in temperatures is fairly well known, so that's not a controversial area. And if you look at these tables, everyone comes up with what seems to be a random number for ECS, so it doesn't really help that much. But anyway, here comes Professor Hansen to the rescue. This is what he says about it. If knowledge of ECS was based only on models, it would be difficult to narrow the range of estimated climate sensitivity, or to have high confidence in any range. Nobody likes the models, because we do not know how well feedbacks are modelled, or even if the models include all significant real-world feedbacks. And then he goes on to say, like the other scientists are coming around to, that really it's best to do it through Paleoscience, by looking at what's happened in the past. Data on Earth's paleoclimate history are so valuable, they allow us to compare different equilibrium climate states, knowing that all feedbacks were in operation. The most accurate evaluation of ECS is from comparison of recent glacial and interglacial climates, because atmospheric composition is known precisely from the ice cores. And now we have to have a quick diversion into the science of ice ages, because this is probably the most interesting part of the video, and also you need to know it to understand the next part. Every climate change denier knows Earth's climate is always changing, and we've had ice ages, and we all know that the ice ages and the warm periods are governed by what's called the Milankovitch cycle. And there are 3 aspects to this. There's what's called the precession, the obliquity, whatever that is, and eccentricity. The thing you really need to know is, to understand this, whether you're in the coldest part of the ice age or in the warmest part of the warm period, the amount of sun arriving at planet Earth is almost exactly identical. The only thing that happens is during an ice age, the southern hemisphere tends to get more of the sun's energy, and in a warm period, the northern hemisphere tends to get more energy. So when an ice age starts, the southern hemisphere gets more sun than the north. The northern hemisphere contains more land, and more of that land is at higher altitudes. So as it gets less sun, ice forms on the higher altitudes, on the tops of mountains. That ice reflects the sun's energy back into space, which leads to cooling. When it rains, some of that water is frozen as the ice develops, less of it goes back to the oceans, so sea levels go down, and so there's more land available for plants to grow, and so the plants take more CO2 out of the atmosphere, which cools the atmosphere. And also, as the oceans cool, a cold ocean is much better at absorbing CO2 than a warm ocean, which is something the United Nations doesn't take into account in its future predictions of how much CO2 the oceans will be able to absorb. As they get warmer, the theory is they'll be able to absorb less CO2. The UN, as far as I understand it, doesn't take that into account. So anyway, have you noticed, if we were to use my world famous zero dimension energy balance model, it wouldn't show any change in temperature. For it doesn't care what part of planet Earth receives the heat energy from the sun. All you tell it is how much heat energy is arriving from the sun and landing on planet Earth. The only things that change are the amount of CO2 and the amount of ice. I think ice is thought to account for about half of the cooling or the warming, depending on which way you're going, and CO2 is about 33% of that cooling or warming. So have you noticed something there? All that temperature increase, which is probably about 6 degrees Celsius between the coldest glacial time, coldest ice age, and the warmest warm period, 6 degrees Celsius of average temperature difference. All of that comes from feedbacks, pretty much from ice sheets on the land and from greenhouse gas changes. That's how sensitive planet Earth is to climate change. The exact amount of sun in a slightly different place leads to all these positive feedbacks, and suddenly it's enough to lower temperatures by 6 degrees Celsius. Wow. There's a big bird up there. Hang on. Ah, that was exciting. So where was I? Back to the dull video. So that's how sensitive Earth's climate is. Exactly the same amount of sun, all the other things fixed, but the sun's energy falling in a slightly different place. Suddenly it's enough to change the temperatures to generate a 130 meter fall in sea levels, or rise if you're warming, and 6 degrees Celsius changing temperature, with no one adding any greenhouse gases or anything. It's all done feedbacks. And have you noticed the feedbacks that are causing this a massive amount of cooling or heating are ice sheets on land and greenhouse gas emissions, which are feedbacks. Well, these are the two feedbacks that are explicitly excluded from calculating equilibrium climate sensitivity, because people just want a generic value that can be used in all circumstances. When people say, why don't the United Nations include the feedbacks from ice melting when they calculate the rate of warming, it's a very good question, because even without humans trying to destroy the world, the ice sheets and the CO2 that results in growing ice sheets, or disappears because of growing ice sheets, is enough to change the climate quite a bit by itself. Now we get back to Professor Hansen and his work to explain to us what's happening with climate change, and warning us that we could be heading for higher temperatures. This is what he says. The last glacial maximum, the last ice age, to the Holocene period. So you start off with a period where you know Earth is in equilibrium and its temperatures are steady, which he's starting off with from an ice age, and then you go to a warm period, the Holocene, before the part of the Holocene before humans start interfering with it, which is another place, a higher temperature, but it's stable temperatures. And then you look at the change of surface albedo, the amount of ice, the amount of vegetation, and the amount of continental shelves exposed by lower sea level in glacial times, and you can see how much temperatures have increased, how much CO2 was in the mix, and you come up with your estimate. And he's done that twice, once between the last glacial maximum and the previous glacial maximum and the warm period, which is called the Eocene. And the warm period, the Eocene, was so warm that there were hippopotamuses living in the Thames in Britain. Now, can you see what he's doing? This is why you have to be very clever to be a climate scientist. He's calculating ECS, equilibrium climate sensitivity, which excludes, by definition, any feedbacks from ice or resulting greenhouse gas emissions. And he's calculating it during a period from which all the warming comes from ice sheets on land and feedback greenhouse gas emissions. You have to be quite clever, and the United Nations warns you. It says, if you don't exclude these very carefully, we call this Earth system sensitivity, which you can tell how important that is. In the Working Group 1 report, there are 606 mentions of ECS, the official United Nations measure for these things, and only 5 mentions of Earth system sensitivity. And all of those mentions say, do not use Earth system sensitivity, even though it includes ice feedbacks and greenhouse gas emissions, which Professor Hansen, in a minute, spoilers, in a minute Professor Hansen is going to say we ought to be including these things. And Professor Michael Mann, if you saw the previous video, believes the same, that there's good reason to include ice sheet feedbacks in calculating future warming. He does a lot of very clever stuff. I'm struggling to understand it all, but we'll just trust him without getting into the maths too much. He comes up with his value. We conclude ECS is approximately 4 degrees Celsius and is almost surely in the range 3.5 to 5.5 degrees Celsius. The IPCC Assessment Report 6 conclusion that 3 degrees Celsius is the best estimate for equilibrium climate sensitivity is inconsistent with the paleoclimate data. Professor Hansen has equilibrium climate sensitivity at 4 degrees Celsius for a doubling of CO2 concentrations in the atmosphere, and he believes it takes 1 watt per square metre to achieve a 1 degree Celsius increase in temperatures. ECS is 4 degrees Celsius, therefore doubling CO2 causes 4 watts per square metre of forcing or additional heating on Earth's surface. To generate 1 degree Celsius of warming from increased CO2 levels, it takes 1 watt of heat energy per square metre of Earth, and they call that forcing. 1 watt of forcing per square metre to have 1 degree Celsius increase in temperatures, which we'll see is important later on. There's nothing revolutionary here. Although the United Nations thinks that ECS is 3 degrees Celsius, Professor Hansen's suggestion of 4 degrees is well within their range of what they consider to be likely values for it. The important thing is, though, Professor Hansen has calculated this using traditional mathematics, and he's published it, and anyone who's clever enough can look at, and they can see if they agree, or they can try and find errors in his work, or maybe come up with alternative suggestions. And that's, even if somebody proved him wrong, for Professor Hansen that would be good news, because as a scientist all he wants to get to is the truth. So if he's made a mistake, someone can help him by correcting him, great. If he hasn't made a mistake, then people will be able to say, the new value for ECS is 4 degrees Celsius. Not like the climate models, where no one's really sure what they include or how they come up with their calculations. So far, everyone's been very clever about calculating the warming effect from doubling CO2 by including fast feedbacks and excluding slow feedbacks. But if you just look at the rate of warming, or the amount of energy so far being added to Earth's systems by the greenhouse gases that are already in the atmosphere, then it turns out we're already at that point that the forcing from the greenhouse gases that are in the atmosphere, using the maths just then without any feedbacks, is enough to cause 4 degrees Celsius of warming, which is ECS 4 degrees Celsius. Now we come to the exciting part. Here is a chart that shows the temperatures for the last, the last 4 ice ages, and the temperature is in red, and that's had to be adjusted because these temperatures have come from the Antarctic, which is very cold, and we need to account for the what's that thing? The equator, which is very hot. So anyway, it's been adjusted. And also in the same chart, Professor Hansen has shown the amount of extra heat greenhouse gases were causing to be applied to Earth's surface to warm the surface. You have to read the chart quite carefully. So you've got temperatures on the left, which apply to the red line, and you've got forcing, you've got the amount of extra heat on the right, and that's represented by the green line. Now, do you think Professor Hansen has done the chart this way because he wants to save paper? Or do you think he's done it this way because he wants to show how tightly coupled the temperature and the amount of heat energy are, how tightly coupled they are, and how they almost follow each other exactly? This is an important thing, because on the right hand side of the chart, he's expanded it a bit, so he's squashed in the Ice Age periods so you can fit them all in, and on the right hand side of the chart he's expanded the axis a bit so you can see it more clearly. As we know, we're at 4 watts per square metre of extra energy being applied to Earth's surface just from the greenhouse gases, possibly more because of all the feedbacks and things like that. And you can see that green line, it goes up, that's the amount of extra heat the greenhouse gases are causing. And you can read it off on the right hand side, and it says it's 4 watts per metre squared, which is where we are now. If we imagine the red line is going to come up and join it, as it has for the rest of the Ice Age, for the last 400,000 years, in theory then, if you track along to the left hand side to show the temperature, when the green line is at 4, we should expect sooner or later the red line, the temperatures, to arrive along with 4, and if you trace it along to the left hand side, you can see that maps onto a temperature increase of 10 degrees Celsius. In theory, we're already on track to reach a temperature increase of 10 degrees Celsius if the amount of CO2 and other greenhouse gases in the atmosphere remains the same as they are now. It's quite possible they'll increase, but you might say, well, maybe they'll go down, maybe we'll go to net zero. The amount of greenhouse gases will start to decline because hopefully the oceans and the plants will absorb CO2, and so temperatures will start to go down. Do you remember what the United Nations objectives are for climate change? To try and arrive at a temperature increase of 1.5 degrees Celsius, which really is going to be 2 degrees Celsius, because 1.5 I think is, if it's not impossible, it certainly is very difficult. Get to 2 degrees Celsius of warming at the moment, or in the near future. How much CO2 are they expecting to have in the atmosphere for that level, and how many watts of forcing per square metre are they expecting to have? And you might think to yourself, well, surely, if Professor Hansen's maths are to be believed, if we have 4 watts per square metre of extra energy for every metre on planet Earth, for every square metre of energy on planet Earth, then we should only expect to get to 4 degrees Celsius of warming, because that's the ECS value, the Equilibrium Climate Sensitivity Model value. But remember, that doesn't include feedbacks from ice sheets or from greenhouse gases which have been added because of the forcing, because of the warming. This value is the Earth system sensitivity. This includes the effects of the ice sheets and the extra greenhouse gases, and they're at not 4 degrees Celsius, at 10 degrees Celsius. Whenever somebody says, why don't the United Nations include the ice sheets when working out their future temperatures, it's a good question, and according to this research, they should do, shouldn't they? So this will be a question for a future video. Professor Michael Mann also says there's good reason to believe that taking into account the feedbacks from ice sheets do make a difference. And here Professor Hansen explains it himself. Earth system sensitivity is the complete climate sensitivity in which the climate system, including greenhouse gases and ice sheets, which we refer to somewhat misleadingly as slow feedbacks, responds to the imposed forcing, the imposed heating. It's the full. Since we no longer need to know, is climate change happening and is it being caused by humans, but we want to know, will there be any food and what will the future be like? Really, we should be using Earth system sensitivity. But if you look again at this chart, you can see the purple line shows where temperatures are now. So there's a bit of a delay, isn't there, between the extra heat being applied to planet Earth and the temperatures catching up. Remember from the beginning of the video that with a large amount of forcing, it takes time for Earth's temperatures to respond. Professor Hansen has come to an understanding of that again, and here he says the timescale of climate feedbacks is crucial but poorly understood, especially for unique human-made forcing. Such forcing is larger than estimates of forcing that drove the largest known rapid global warming, the Paleocene Eocene thermal maximum, the PETM it's quite often called, which occurred 56 million years before present. And that's important because if you've got a small amount of heating, maybe 0.2 watts per square metre, which I think was happening during the PETM collapse or during the Ice Age transitions, 0.2 watts is quite small. Earth's energy imbalance is never that great, so Earth is almost nearly keeping up. If instead you've got a lot of humans putting huge amounts of CO2 into the atmosphere, causing 4 watts per square metre of extra heat energy being applied to the Earth's surface, suddenly Earth's energy, it really is out of balance. And this response time between the energy being applied and the resulting increase in temperatures is much bigger, and it becomes much more important. And Professor Hansen has tackled this by using a climate model. And he might say, well, I didn't think anyone liked climate models, and they're full of faults and nobody knows what they're doing or what they include or what the algorithms are. Well, that's true, but Professor Hansen is using the Goddard Institute of Space Studies model. That's where he was based there for 30 years, and I think he's still got a role there. I think he's a director of some department there. Every day, the Goddard Institute of Space Studies, which ironically has become famous for its Earth studies, it uploads its source code for its climate model. It looks as though it's written to run on the Unix operating system, and it's written in the C programming language, but anyone can go and look at it. I've downloaded it onto my phone, although I haven't tried to run it yet. And it might sound like a flippant thing to say, but if you have a modern powerful smartphone, maybe like one of the top iPhones, your phone is more powerful than supercomputers were 35 years ago when Professor Hansen came up with his climate model, which was powerful enough to accurately predict the temperature increases between 35 years ago and now. So that's something to think about. When the climate scientists talk about a response time, they measure it in how long it takes to get to what they say is 1 over the mathematical constant E, which is Euler's number. Effectively, it's 37% of the warming or the forcing, in the same way as radiation decline is measured in half-lives. The climate scientists measure the progress of forcing or temperature increases in how long it takes to get to 37% of its eventual value. And Professor Hansen, being the clever person he is, he says 10 years for planet Earth to lose 37% of its energy imbalance, which is because planet Earth will be warming and it will be emitting more heat into space, and it will eventually overcome the amount of greenhouse gases that are trapping the heat. And so you've got 37% of the way there, so the amount of heating will be less than it was 10 years ago, after 10 years. But he says to reach 37% of the final temperature will take 100 years. Even though the forcing drops quickly, Earth continues to warm for some time. Although Professor Hansen has a higher value for the equilibrium point, 4 degrees Celsius rather than 3, it doesn't mean that temperatures will rise more quickly, but that they may continue to rise for longer, because they've got to reach a higher temperature. We've still got an enormous carbon budget, which we think we can put into the atmosphere, and then we can keep that level by getting to net zero and then possibly taking some CO2 out of the atmosphere. Already, according to this, we're already committed to an increase of nearly 4 degrees Celsius in the next 100 years, and even then temperatures won't stop increasing. According to this chart, unless there's a significant reduction in greenhouse gases in the atmosphere, Earth would continue to warm for nearly 1,000 years. Here we get to his summary. The CO2 increase that drove the PETM, the Great Extinction Period, 56 million years ago, that drove the PETM global warming was introduced over a few thousand years. The net human-made climate forcing has been growing rapidly only since 1970, i.e. for about half a century. But within another century it could match or exceed the PETM forcing, while being introduced 20 times faster. There is no known paleoclimate analogue for such forcing. So that's the end of the most interesting part of the video, if you can call it interesting. There is one more bit I'm going to include. There's several other parts Professor Hansen includes in his research, including things like ultra-fast feedbacks by the effects of clouds and all sorts of other fundamental parts of climate change. I think we've suffered enough for one video, but I just want to cover something that might impact us in the next 10, 20, 30 years, and that's, at the moment, there are a lot of aerosols in the atmosphere which are put there by burning of fossil fuels. Nobody really knows how much aerosol there is in the atmosphere, because you can't measure them accurately with satellites. They don't travel all that fast, so they don't really show up in the ice sheets, ice cores, unless it's from a volcano which throws its aerosols high up in the atmosphere and they go all the way around the world. Or from ancient times there was an awful lot of lead being smelted, and you can almost track ancient history through the lead deposits that end up in the ice cores. Anyway, you can't really track aerosols in that way. This is what Professor Hansen has to say. Aerosol climate forcing is difficult to measure because it occurs mainly via small induced cloud changes. The absence of significant global warming over the period 1850 to 1920, as shown in the United Nations report, is a clue for the scale of aerosol forcing. Greenhouse gas forcing increased the energy being applied to Earth's surface by 0.54 watts per square metre between 1850 and 1920, which causes an expected warming of 0.3 degrees Celsius by 1920. But it didn't do that, it was flat, possibly because of all the aerosols being put into the atmosphere. And he's concerned because 1970 was what he calls a hinge point. The Western world cleaned up its air, it caused an increase in temperatures, which you can see in the graph. Everyone keeps complaining about China building coal-fired power stations. In the next decade, China is on a mission to reduce its fossil fuel emissions. We could be heading for another hinge point where temperatures will increase even faster, because NASA, for example, estimates, although we're at 1 degree Celsius of warming officially, if you were to remove all the aerosols from burning fossil fuels, it would add an extra 1 degree Celsius. Basically, what he's saying is, if we reach net zero, and we think, well done, we've reached net zero, there's hope for us all, suddenly we'll have an extra 1 degree Celsius of warming because we'll have lost all the aerosols. So I just wanted to include that because that's a more immediate thing to take into account. That's the end of the video. In case anyone is still watching, and if you are, well done for sticking with the video. I've made a summary of the issues I found. So the response time is not accurately known. Warmer oceans absorb less CO2, which is not taken into account by the United Nations. Earth sensitivity is a better measure to use than equilibrium climate sensitivity. And humans and aerosols have been affecting the climate for longer than thought. It's quite possible those aerosols have a much bigger impact than people realise, but there's no point in studying them for much longer, because in the next decades we're going to find out. So in a future video I'm going to look at why is it that concerns like this, everyone's always telling me, why aren't the ice sheets included in the feedbacks for the United Nations report? In a future video we're going to look at that. But I shall finish off now by a quote from someone who works for ExxonMobil, and I think it's quite apt. The critical problem is that the environmental impacts of the CO2 buildup may be so long delayed. A look at the theory of feedback systems shows that where there is such a long delay, the system breaks down. They're very clever, the people who work at Exxon, aren't they? A bit too clever by half. Ooh. I'll be back with you in a minute.